Alright, this video is coinciding with chapters 8, 1A and B, which is pretty much talking about precipitation reactions and how to predict the products of a precipitation reaction. So as you read, hopefully, that you saw that one of the driving forces of chemical reactions is the formation of a solid. Okay? Now, with a precipitation reaction, what this pretty much turns out to is we have an aqueous ionic compound combining with another aqueous compound, and it's going to form a solid, okay? And then most likely another aqueous compound. Now, what I'm meaning by that is we have a positive, let's go ahead and change color a little bit here. All right, let's go ahead and say we had this positive and this negative, and then here we have this positive and this negative, right? And as it turns out, when I have those two positives and those two negatives in solution and I mix them together, there's always a chance that, like, for example, this attraction right here between one positive and the other's negative, or one's cation and the other's anion, that attraction might be stronger than how hard the water is pulling on the molecules to keep them in solution or keep them dissolved. So what will end up happening is we end up with a solid compound which will have a one substance here. So for example, if I was to go silver chloride, right? But anyways, this right here is a solid, right? Leaving the negative ion and the green anion and the red cation still floating around in solution. Okay, so this right here is going to result in a solid forming. Now, the trick to this predicting a precipitation reaction or predicting precipitation products is the use of the solubility rules. Now, remember, solubility is referring to the ability for something to dissolve in water at a certain temperature. Well, the temperature that we're going to focus on is based on a table, okay, a solubility, not a solubility curve, but a solubility rules table at 25 degrees Celsius. And it looks a lot like this, okay? I'm a little short here. Let's fix this. There, that's better. So, you are only going to be responsible for these 6 rules. I'm going to talk about some of the exceptions and how to read this, but what you're mainly needing to look at is that these rules, unless they are objected by another rule on this table, we are going to assume are absolute. So for example, if I was to have a substance, right, I need to know if the substance is going to dissolve in water or not. If it'll dissolve in water, then it will stay aqueous and will not form a solid. But if I combine, say, a certain cation with another anion and they're insoluble, then that means I would form the solid, right? So the solid means that it is insoluble, and then the aqueous means that it's going to remain soluble in solution at 25 degrees Celsius. So, taking a look at this, we have the nitrate ion, right? And I'm gonna, like I said, I'm gonna stick with just the stuff that's on this page. So if we're looking at the polyatomic ions, nitrates, ammonia. So here we have nitrate right here. We have ammonia. Let's see, we have sulfate, right? The sulfates here, hydroxides, okay, carbonate, phosphate, sulfide. Well, sulfide is not really a polyatomic, but those types of polyatomic ions are going to be ones that I'm really paying attention to when it comes to this particular part of the unit. Okay. So I'm not going to ask you what's the solubility of an acetate or what is the solubility of a peroxide. Okay, you won't have to worry about those. It'll just be these guys that you have on the board right here. Looks like we have 1, 2, 3, 4, 5, 6 polyatomic ions that are really going to be involved in these types of reactions. Okay, so does that mean that I don't want you to know what an acetate is or don't want you to know what a peroxide is? Of course not, right? You should still know what those polyatomic ions are because those were one of the early ones that I mentioned that I'm going to use often. So hopefully by now you have a good idea of what they look like and what their charge is. But like I said, regarding this stuff, you're only going to have to worry about these polyatomic ions and follow the rules with these polyatomic ions. All right, so let's go ahead and clear this up here. All right, now, the first one. Most nitrate salts are soluble, meaning if there's anything that has a nitrate on it, it's going to be a soluble compound. Anything from lead nitrate to mercury nitrate to potassium nitrate, sodium nitrate, okay, nitrates are soluble. So if you see nitrate, it's going to be soluble. It's going to stay in solution, okay? Most salts of sodium, potassium, and ammonium are soluble, okay? So looking at things like sodium, potassium, ammonium, okay, I'm going to add a little thing right here. I'm going to add lithium, right, which is plus. And I'll also add rubidium plus and cesium plus because those are all the alkali metals. So pretty much most salts of alkali metals and ammonium are soluble. Okay, so I'm adding that to right there. Okay, most chlorides, now with the chlorides, I'm going to also add the other halogens because they happen to follow the same rules. So I want you to be adding things like the fluorides, the bromides, and the iodides. Okay, those are also ones that you're going to have to know. Okay, but it's not that hard considering that chloride salts, fluoride salts, bromide salts, iodide salts should behave similarly. Okay. Now, with number 3, it says most chloride salts are soluble, notable exceptions, meaning these particular examples are not soluble in water. Those being silver, lead 2, and mercury, um, the mercury 2. Okay, so those guys right there are going to be um, insoluble, whether they be a fluoride, a chloride, a bromide, or iodide. Okay, you won't see too much of this guy right here, I'll let you know, but silver and lead do definitely stick out, and you should know that. So the lead 2 and the silver ions are not soluble chlorides or fluorides, bromides, iodides, from, on and so forth. So let's clear that out a little bit. Okay, most sulfate salts are soluble. Okay, the notable exceptions being barium sulfate, lead 2 sulfate, and calcium sulfate. Okay, so in any case, all sulfates are going to be soluble. Sulfate is SO4 2 minus, right? So any SO4 2 minus is going to be soluble except these 3 right here, the one of calcium, lead 2, and barium. Are you going to need to have this thing memorized? No, you're not. I'm going to give you access to solubility rules. Okay? Obviously, if you know them well, then it'll take you less time to do a problem, but if you need to refer to them, they're here for you. Okay? Most hydroxide compounds are only slightly soluble. And let's just go ahead and change that right now. Okay? They're insoluble. Period. Right? Hydroxide compounds are insoluble. The important exceptions being sodium hydroxide, potassium hydroxide, okay? Barium hydroxide, and they say they're moderately soluble. No, let's just go ahead and get rid of that moderately and just say, you know what, they are soluble. Okay, so hydroxides are soluble except potassium and sodium. And the reason why potassium and sodium are exceptions is because they're going to contradict Rule 2, which says that sodiums, potassiums, and ammoniums are soluble. That's why those are going to be soluble, okay? The barium and calcium, those are just 2 examples of soluble exceptions. Now, in the same breath, if I was to have lithium hydroxide or rubidium hydroxide, right? Lithium hydroxide, rubidium hydroxide, or cesium hydroxide, those would also be soluble because Rule 2 states that it's pretty much the alkali metal. So if you have the alkali metal cation, it's going to be soluble, okay? Even if it contradicts another rule. And then lastly, number 6, most sulfides, carbonates, phosphates, sites are slightly soluble. No, they're not. We're just going to say that they are insoluble. And of course, the exceptions being, okay, even though they're not mentioned right here, The exceptions being the ions listed in number 2. So sodium sulfide, potassium sulfide, lithium, rubidium, cesium, ammonium sulfide, and then all of those carbonates, those phosphates, those are all still going to be soluble because they have a contradiction. Okay? So, taking a look at what a problem would look like, let's say, okay, let's look at ammonium chloride and lead nitrate. So those are my 2 reactants. Okay, and I may give you those 2 and I'll say, what are the products? Or I may just say write the balanced chemical equation, and in this case you need to make sure that you include if something is aqueous or if something is solid. Okay, so ammonium chloride is NH4Cl, and lead 2 nitrate is Pb, okay, 2, and each nitrate has -1, so there's my lead 2 nitrate. And I need to form a product, right? And I know what my products are. And pretty much when you have precipitation reactions, it's as simple as, it's honestly as simple as this. I have or I guess you should do this. It should be cation, anion, right? And then cation, anion, and I just flip them. So now I'm going to reorder the cation. So I'm going to have my red cation with my green anion and my green cation. Oops, hey, that's not green. My green cation with my red anion, right? So I'm just having them switch places. So as they switch places, I'm going to end up with ammonium with nitrate, and I have ammonium and nitrate, so NO3, since ammonium is +1 and nitrate's -1. And then I have lead chloride. In this case, lead 2 chloride, PbCl2. Okay. Remember, I need lead chloride to be, because lead's 2 plus, chloride's -, or -1, -. So, looking at this, I need to identify whether or not they are, this would be my products. Now I got to see what their state is going to be. Okay, ammonium chloride, if I follow the rules, okay, ammonium chloride is going to be aqueous. Okay, lead 2 nitrate is going to be aqueous, right? Ammonium chloride is going to be soluble for, let's see, the reasons being number 2 and number 3. Okay, rules 2 and 3 support why ammonium chloride would be soluble. And then lead nitrate, number 1, rule 1, most nitrates are soluble. Okay, you can always say all because they're all soluble. All right, so we know those are soluble. And then brings us to our product side, ammonium nitrate. Well, if all ammonium salts are soluble and all nitrate salts are soluble, well, then it only makes sense to say that, that's horrible. It's only sense to say that that would also be aqueous and stay in solution. But now the lead chloride, if you look at the exceptions for chloride for rule number 3, okay, one of the exceptions is lead 2 chloride. So this is a solid. Okay? So if I was to rewrite my overall equation, it would look like this. NH4Cl aqueous plus PbNO3 2 aqueous forms NH4NO3 aqueous plus PbCl2 solid. Now, of course, there's one key component missing here, and that is you need to make sure it's balanced. Okay, so in this case, if I was to balance it, the nice thing about balancing with polyatomic ions, if they show up in the same place, you can treat them as if they were one thing. Remember I tell you when they're ionized, you got to treat them as they're one entity. They're one, nitrate, NO3. I can't split that NO3 up. Well, I also can't split this NO3 up either. So here I have, right here, I have 2 NO3s. Okay, so that means I need to have 2 NO3. So 2 here will distribute to that NO3. Okay. That'll also mean that I need to have 2 ammonium. So 2 ammonium here. And then that results in having 2 chlorides as well. And I actually already have 2 chlorides over on my product side, so that's good. So I have 2 ammoniums, I have 2 chlorides, I have, let's see here, lead, I have 1 lead, and then 2 nitrates and 2 nitrates. So this is my balanced chemical equation. And that would be how to do a problem of predicting the precipitation reaction. So I'm going to go ahead and give you one. I want you to work it out, and then I will pop the answer up, and hopefully you get it right. If you don't, then make sure you see me so we can fix it. Okay, I actually gave you a couple of them. Okay, so like I said, try both of these out. Right, pause the video, and then I'll write the correct answer. So the first one is, if I take barium iodide and I mix it with an aqueous solution of barium iodide, and I mix it with an aqueous solution of potassium sulfate, what's my reaction? Am I going to have a reaction? What are my products? Okay, same thing with the next one. So, sodium hydroxide with lithium bromide. Right, if I mix those together, what's going to happen? Am I going to form a solid, or am I not going to form a solid? Okay, so I'm pretty much asking, is there going to be a reaction? Because here's the thing. If my products are still aqueous, both of them, then nothing really happened. All I did was just put a whole bunch of ions in water, and nothing's happening. Because if there's no solid forming, then there's no reaction that took place. So keep that in mind. All right? So go ahead and pause the video and then work them out, and then I will give you the answer. Okay, so there are your answers. Okay, balanced chemical equations. As you can see right here, a solid does form with the barium sulfate. And as you can see down here, there is no solid forming. So in truth, no reaction took place in the second one, but there was a reaction here. Okay, if you didn't get those right, then by all means, come on in and we'll get you helped out. All right?